Now as I told you, what is space? Time is in one dimension, space is in two dimension. Now varies with dependent or independent variable. Now what is the concept of dependent or independent? If I draw this signal, it has two variables. Namely, if I say x of t, this is one axis, this is another axis. So when I say x of t is equal to suppose a sine of omega t, it may have another variable, say phi also. Here in this case phi is 0. So there are different variables in this signal, namely a, namely t, namely phi. So what is the dimension of the signal? The dimension of the signal is that it is one dimensional signal. Now why we are saying that it is one dimensional signal? Although the number of variables are 1, 2 and 3. So the dimension of the variable, dimension of a signal is not based on how many variables it has, but the dimension of the signal is been decided by how many number of independent variables it has. If you could see to this signal, phi is one variable. Fortunately here it is 0, incidentally here it is 0. Another variable is this axis of amplitude, another variable is this axis of time. But what we see, that is amplitude is dependent on time, right? So this time is the independent axis. So number of variables may be 10 in a particular signal, but if the number of independent variable is 1, then we say that it is a one dimensional signal. Same case, if you see here, if I say this is a point, let us say that we have an image, we have a photograph. So let us say even this particular board is a photograph. So suppose this we have a pixel at the position x comma y. So this is x and this is y. Position is 0 comma 0. Now the number of variables in this case can be many. Intensity, the brightness, the color, the contrast, there can be so many variables on this. But what are the independent variables? Is this particular x and y. This particular location, say y1 and say this x1, for this particular pixel is going to be fixed. Therefore we say that these two are independent variable. It doesn't depend upon whether it is bright pixel or it is dark pixel or the intensity pixel is more or less. So this is a two-dimensional signal. Therefore an image is also known as a signal, but it is in two dimension. Okay, so this you are going to learn in the final year when you have a subject known as image processing. But these concepts of signals and systems will be clearly used there. So as far as signals and systems is concerned, we are all going to discuss about one dimensional signal only, and all the signal will be dependent on time as an independent variable only. So we are not going to discuss lot many things. Our intention in signals and systems is to learn the operations on the signal rather to learn different dimensions of the signal. So the dimension or the independent variable is going to be time only, and we are going to learn different operations on this particular type signal. Okay, so now we have defined signals and we have seen the concept of dependent and independent variable also. Now let us see the classification of signals, which is the first chapter of unit 1. So as I told you, we are going to define or we are going to take different classifications. So first is continuous and discrete time signals. Now it has to be understood that this classification of signals, certain classification is been done based on the amplitude and certain classification is done based on the time axis or based on the independent axis. Now as far as this continuous and discrete time signal is concerned, it is both. Now how it is? When I say continuous time signal and if I draw it, okay. So if you could see A is the maximum amplitude of the sinusoidal signal. This is amplitude axis, this is time axis, this is origin. So we say x of t is equal to a sine of omega c. Now why we say it is continuous time signal? Because the value of the signal is defined at all values of time. At all values. Say time t is equal to 0, say time t is equal to, even here suppose here it is 0.1, 0.2, 0.3, here even at 0. So the value of the signal, it may be anything, it may be 0. 0 is also in value. 0, 1, so it is defined at all values of time. So therefore we say it is a continuous time signal. It has nothing to do with the nature of the signal. The nature of the signal can be anything. The amplitude of the signal can be anything. But point is that the value of the signal is defined for all values of time. So we say that it is a continuous time signal. Even this signal particularly, if I say this, Now this is a rectangular signal. So mathematical definition of rectangular signal, we'll be seeing it in second chapter in basic signals. So this is also a signal where the amplitude of the signal is defined for all values of time. Now you may ask how? It is defined only from say minus tau to tau. So for this particular time it is defined A. For other time it is not defined. It is defined and the value of the signal is 0. So yes, so this is known as a continuous time signal. Even this signal particularly, now this is an exponential signal. Say the amplitude of this is B. How would we define it? It is y of t. So B into e raised to at, and I would write minus at because it is exponentially decaying. So this is also a continuous time signal. So what is the point of continuous time signal? That if you take it any value of time, say 0, 0.1, 5, 0.10, 100, 1000, for any values of time, the value of the signal is defined. So this is known as a continuous time signal. So the continuous time signal means for all values of the time, for all values of the time, the signal depends, or the signal has a finite value of amplitude. So that is what is a continuous time signal. Now let us see the other part of this, which is discrete time signal. So let us see another classification, which I told you is discrete time. So if you have the signal something like this, now if you could see, the lobe of the signal resembles the lobe of a sine wave, or it can be even an exponential wave of any regular signal. But what is the point of importance here is to see that the signal is defined only for particular values of time. Say it is defined at n is equal to 0, it is defined at n is equal to 1, n is equal to 2, and so on. So 0 it is the value is 0. For 1 the value is suppose this, whatever it is, so 2. For 2 the value is suppose 4. For 3 the value is 5, and this goes on. But if you ask me what is the value of the signal at 1.2, I cannot say you that the value of the signal at 1.2 is 0. The value of the signal is not defined only. So the value of signal is defined only for integer values of instants. So 0, 1, 2, 3, 4, 5. Generally this is integers. Okay? Generally it is integers. So it is defined only for these particular values of time. So when the value of the signal is defined for particular instants of time, so this is known as a discrete time signal. Or the discrete word has come. Discrete means something which is not very common, which is not very continuous. It is only for particular time. Okay? So when the value of the signal is defined for discrete instance, or say particular instance of time, so this is a discrete time signal. Okay? Now this has a nature of sinusoidal signal, that may be there. It is not compulsory, it has to be a nature of sinusoidal signal. Now another type of discrete signal can be this. So let us say y of n is equal to this. So it is defined only for 0, 1, 2, 3, 4. So it is defined only for 5 instants of time, and the amplitudes of them are relatively 1, 2, 2, -1 and 3. This is known as a discrete time signal.